Okay, welcome to Unit 1 review for the PhD, powers and roots. The first outcome is the exponent laws. So we take a look at example 1 here with the example A. We've got our base is x exponent 4 times x exponent 5. We get x exponent 9 because what are we doing? We are adding exponents to get our final answer. So we multiply same bases, meaning we add exponents, okay? We just change that multiply to a plus. We add those exponents. Then we go to the second law. The second law is the opposite of the first law. So we divide the same base. We're going to do the opposite of adding. We are going to subtract exponents. So this time I've got x exponent 7 dividing by x exponent 2. And again, when we divide, we're going to take the exponents and subtract them. That's going to give us our x exponent 5. All right. Now our division sentences can be written like that, left to right, or it can be written as a fraction. If it's written as a fraction, we still do the same rules. So we take all the exponents and we would subtract them. And so 11 subtract 7 is exponent 4. That's how we get our w exponent 4. Okay, we're going to move to our next law. So, letter C, our next law is power of a power. Now, with our power of a power law, we always have brackets. All right, so here's an example. If I've got x exponent 3, and on the outside I've got a 4. What do you think the brackets there and the exponent inside and outside, what do you think's going on there?
The 4 and the 3 are going to combine together.
You're exactly right. The 4 and the 3 are going to multiply. So because we've got brackets, we're going to multiply those. So we're going to get x exponent 12. Now we can write that out as repeated multiplication if you find it easier. So what you would do, the 4 outside is telling us something. It's saying we've got 4 of x exponent 3. So that means we've got x exponent 3, x exponent 3, x exponent 3, we've got 4 of them. And then now if they're timesing side by side, we could do it this way where we add the exponents. We're going to get the exact same answer, okay? So this is the long way to do it. You expand it out. The short way is to just take the exponent outside and multiply it to every exponent inside. That also removes the brackets. You have to remember that. That removes your brackets. Okay. D is very similar to C. Only now I'm going to put a couple things inside the brackets. So I'm going to put, let's say I'm going to have an x and a y. So x squared, y cubed, all exponent 4. Well, in this case, we do the exact same thing as we did with the example above. We could write it out like we did with the blue ones. So we would have 4 sets of x squared, y cubed. Or we take the outside exponent, and he's going to multiply to every exponent inside. And that's how those happen. And again, it's going to remove the brackets. So we're going to have x and y. What is our exponent on the x? 8. Good. What is the exponent on the y? 12. Beautiful. All right. Make sure that your exponents kind of go up on their top right. Okay? They can't be written side by side. Okay? Make sure you're writing them correctly. Okay, so that's called power of a product. Product means there's two things sitting side by side or multiplying inside. Now, what if I put a plus sign between the x and y? Could I use this rule? I put a plus sign right here between the x and y. No. The only thing this works with is if it is multiplying, okay? So the power of a product only works if you're multiplying. You cannot put a plus sign or subtract sign between those. If you do that, then you have to solve it a different way. You are not allowed to multiply that outside exponent in, okay? So the next example is a variation of that one, only instead now it's going to be set into a fraction. Something different on top, something different on the bottom. So this one's called power of a quotient. So quotient meaning it's written as a fraction. So So I'm going to put x on top, and I'm going to put y on the bottom. And then we're going to put some exponents on them. So I'm going to put a 2 on x. I'll put a 3 back on y. And then I'm going to put a 5 on the outside. Well, if I've got a 5 on the outside, just like with the one on the previous example, we're going to take the 5 and multiply it to all the exponents inside. So now we're going to get x on top of y, and we need to write their exponents. So what's 5 times 2? 10, good. And what's 5 multiplied by 3? 15, beautiful. And you're going to notice that it also took away the brackets. The brackets are now gone. Okay? So that's when we've got variables inside. Now we're going to start throwing some coefficients in there. We're going to start putting numbers in there as well with our variables. Okay? And that's going to change the question just a little bit. All right, we got one law left, though. Is it one law? Yeah, I think one law. Okay, letter F. One more law. And this law says that x to the 0 equals 1. So anything exponent 0 is equal to 1. And the reason is because it will always divide by the base with the pattern. So we're going to show the pattern here. So you guys did this review yesterday, showing the pattern. So the pattern, if you remember, goes like this. If I've got the number 3, and I say 3 cubed, 3 cubed is equal to 27. 3 squared is equal to 9. 3 exponent 1 is equal to 3. 3 exponent 0, now let's see what's going to be the answer. It should be a 1, but why would it be a 1? The whole point is this. If we divide by the base number, that's all that's happening here every time. How do I go from 27 to 9? I take 27, divide by the base, I get 9. 9 divided by the base, I get 3. 3 divided by the base gives us 1. So whenever you divide the base low enough, it's going to start giving you anything exponent 0 equals 1. Okay, that pattern will hold true for any digit. Okay? And any variable. So that's the pattern on why it happens. Next, now we got to talk about coefficients. So this is number 2, coefficients. When we talk about coefficients, we're going to start talking about negative bases as well. So, coefficients, the rules all apply. So, example, if I've got negative 2x cubed all to the 4th power, we need to make sure our coefficients are going to match what's going on. Okay? So we can't forget the coefficient is there. So the first thing I'm going to do is I'm going to expand this. The 4 here tells me I've got 4 sets of that bracket. So I'm going to write it out 4 times. So this is equal to negative 2x cubed times negative 2x cubed times negative 2x cubed times negative 2x cubed. So that's what it should all look like.
Can you add all that together?
So now we're going to take a look at our negatives. I want to look at the negatives for a moment. How many negative signs do we have? 4. And what do we know about even and odd numbers and negative signs? Right. So if we have an even number of negative signs, 2 of them, 4 of them, 6 of them, or 8 of them, we're going to multiply and always give us a positive answer. If there's an odd number of negative signs, 1, 3, 5, 7, then you're going to have a negative answer. So we've got 4 negative signs. That means this guy's going to be a positive answer. Now, we have to take a look at those 2's. How many 2's do you see? 4 of them. We have to make sure we multiply 2 by itself 4 times. So we have 2 times 2 is 4, times 2 more is 8, And times 2 more, 16. We're going to get positive 16. Now how many x's do I have? What do you think? 12 of them. Count them, how many we've got. You got to count the exponents, right? Because now we're going to do it the exponent way. We just did it the expanded way. The exponent way is multiply the 4 in, correct? Is that the only spot I multiply the 4 to? No. What's missing that I didn't draw in?
You have to draw them.
The little hidden 1. Wherever we've got an exponent, every digit and every variable will always have an exponent, even if you can't see it. If you can't see it, it's a hidden 1. Only the 1s can hide. So that means that 4 must multiply that 1. Well, and if we look at our example, that makes sense, because that means we're going to have 4 2s, 4 negative 2s. And what do we have? 4 negative 2. That's exactly what we ended up with. So that means that we have to make sure that that exponent also multiplies to the coefficient. Okay, we can't forget that. All right, let's take another example. We're going to do it without expanding it. We're just going to do it using the exponent laws. Okay, example 2. I'm going to move it up a little bit. Okay, we're going to have all right, 3w exponent 4 all squared. 3w exponent 4 all squared. So the very first thing we should do is draw in the hidden exponents. Okay, I'm going to make a little note. Draw the hiding exponents. Well, I've got one hiding exponent right there. He's a 1. Okay, so that's our first step. We have to make sure we put those in so we don't forget them. Now we're going to take a look, and we're going to multiply that exponent now on the outside to every exponent inside. And that's going to remove the bracket. So now, that's going to give us 3 squared w exponent 8. Now, if it says leave it in exponential form, that's how you would leave it. But if it doesn't say leave it in exponential form, and it just says simplify, or expand, or solve, then you have to actually solve the digit part. You have to solve 3 squared. Well, that means I'm timing 3 by itself twice. What's 3 times 3? 9. Good. So we get 9w exponent 8. That will be our final answer. Okay? Check your work. Make sure you have it written down correctly. Now we're going to talk about negative bases and floater negatives. So this is number 3. Number 3. Negative bases versus floater negatives. Okay, negative bases versus floater negatives. So I'm going to give an example of a negative base. Negative 5 exponent 3. That would be considered a negative base. And a floater negative, negative 5 exponent 3. So what do you notice about the floater negative versus the negative base? What do you notice automatically right away, first thing you see? That's right, one has brackets and one does not. But now they're going to show you a couple other ways, okay? So a floater negative could also do this. What's the difference then from example 1 on the left? We're comparing floater negatives to negative bases. How is my second example on the right different from the example on the left? Maya? That's right, the exponent's inside the bracket. So what are these brackets trying to do?
Separate.
Just confuse you, and they're probably just separating you from another term. Okay? So they're meant there honestly to confuse you. They want to know, do you know the difference between this and the one on the left? So basically, these two here, they mean the exact same thing. These brackets mean nothing. Okay, they're placement brackets. That's all it is. Okay? All right, so when I have a negative base, that means when I would write my sentence out in repeated multiplication to solve it, I'm using my negative, the amount of times that the exponent says. Because remember, that exponent has a job, and his job is to tell the base how many times to times himself to himself. So he's going to say, yo, -5, how about you multiply yourself 3 times, please? So that's exactly what's going on. We've got a -5 times a -5 times a -5. That is the job of the exponent. Okay? He's saying -5, multiply yourself, please, 3 times. So now we're going to multiply that -5 and we get a -125. Okay? If we look on the right-hand side, we also get the exact same answer, -125. Who knows why they're the same answer? Okay, there's only one negative on the left. Here we've got one negative sign. And how many negatives do we have on the left? 3. Well, what do we know if we have 3 negative signs? Well, what do we know about 3 negative signs and 1 negative sign? What kinds of numbers are those? They're odd numbers. So if we've got an odd number, we're going to have always a negative answer. So an odd number of negative signs is an odd negative answer. Okay? So, what about an even number of negative signs? Let's take a look and see how that would change our example, okay? I'll give you a minute to write that down. Okay, here's our second example, and this example is going to be with an even exponent. So, again, we have negative bases versus floater negatives. So we're going to have -4. Actually, let's change the 4 to a 2. -2 exponent 4. And then we're going to go -2 exponent 4. So how would I expand it on the left-hand side? How would I write that out as repeated multiplication?
-2 times -2 times -2 times -2.
Excellent. So we have 4 -2's. So how many negative signs? 4 negative signs. That means we're going to have a positive answer. So we're going to take 2 and multiply by itself 4 times. What do we get? 16. Good. That's going to be a positive 16. Let's take a look on the left-hand side. How many negative signs do we see? 1. Does the 4 apply to the negative this time? No. How come? There's no brackets. Okay, well, Miss Tuck says there's no brackets, so that's why. What if I do this? There's brackets. Does it change the answer? No, because the exponent's on the inside. Okay, remember, if it's a negative base, the base only is on the inside. Okay? All right, so these brackets mean nothing to us, so I'm just erasing those. So we have one negative sign here. So the answer has to be a -1, and it'll be the -16. Okay? So that's the difference between negatives being a negative base and versus a negative floater. Okay? All right. The next thing we need to talk about here is square roots and perfect squares and benchmarking. But before we do that, we're going to do a combined law question. We're going to do a couple combined laws like bedmass. Okay, I'll give you a second to write that down. Okay, so let's talk about bedmass questions. Is this number 4 or 5? 4? Okay. So 4 is going to be some bedmass. Bedmass combined laws. Combined exponent laws. Example 1. We're going to go with -2 cubed times -3 squared times negative 2 to the 7 times negative 3 to the 4, all divided by negative 2 to the 6 times negative 3. I'll give you a minute to write that down, then we're going to discuss the question. Okay. So, let's draw in our hidden 1 there. We've got a hidden 1 missing right here. So, whenever we've got a combined law like this, and we see multiple things on top of a fraction and multiple things on the bottom of a fraction, we need to solve the top until we get our 2 separate bases used once only with 1 exponent each. Okay, because our bottom has 2 different bases with 1 exponent each. We want our top to match that. So, what we do is, we either have a highlighter or we can circle them. So the ones that are going to match are the negative 2 exponent 7s, and then the other guys on top that I didn't shade, those are the negative 3s. Those are also going to match. So, I'm going to have negative 2. How big is my exponent on top of my negative 2s? We're going to take the 3 and we're going to add it to the 7 because we're multiplying. Multiplying means add the exponents. So how many do I have on the top? 10 of them. Good. All right. We're going to do the same thing for the negative 3s. Negative 3s. How many negative 3s do I have? On the top, we've got a 2, and we're adding it to the 4. So we're going to have 6. So we've got our top simplified. Now we're going to write the bottom back underneath. Okay, so that's as far as we got there. So now, we take them separately. The blue ones on the left, the negative 2s, they have the same bases. So we're going to take their exponents and we're going to subtract them. So how many negative 2s do we end up with? I have 10 subtracting 6. 4. All right. Now, 3s, I've got a negative 3 base. Move all this to the left a little bit. Alright. So, how many negative 3s do I have? I need to subtract my exponents here. How many do I have left over? 5. Good. Now, if the question says leave an exponent form, this is all you're going to have. Okay? If it wants you to evaluate, you would solve this, then multiply. Okay, so I'd like you to solve both and then multiply. We're going to evaluate for you. Okay, so negative 2 exponent 4, how big do we get? 16. And negative 3 exponent 5 is how big? Negative 243. Now we've got to multiply 16 by negative 243. How many negative signs do you see? 1. So is our answer positive or negative? Negative, good. So we're going to have negative 3,888 or 30880?
3,880.
Okay. Like that? So it's 3 8.
Yes.
Beautiful, that's a cool number. All right. Okay, number 5 is perfect squares and non-perfect squares. So perfect and non-perfect squares. So perfect and non-perfect squares. So a perfect square has 2 identical factors. Okay? Perfect square has 2 identical factors. Before we go to nons, so a couple more things about perfect squares. So they have two identical factors. The answers are always rational, which means a fraction or terminating decimal. Okay, so those are other features of perfect squares. So they have two identical factors and their answers are always rational, meaning they're in a fraction form or can be put into a fraction over 1, or they have terminating decimals, decimals that end. So here's a couple examples before we move on. Okay, so here's an example of perfect square. 25. 25 is a perfect square because its factors are 5 times 5. That's a perfect square. They're identical. Another one. 6.25 is also a perfect square. Now, how do we tell what their answer is if we already know? So if I wanted to find, if I know the perfect squares basically refer to area because we took two numbers like length times width. And then these, the factors, are actually the side lengths. Okay? So if I've got factors 5 and 5, that means my square over here, every side was 5 centimeters long or 5 units long. Okay? That's what that's talking about. So if our area is 25, that means I took 5 length times width, 5. 5 times 5, same answers. Okay, now how would I go from area to get my side length? How did I find 5 from 25? Is it a number I just memorized? Is there a button on the calculator maybe I could push? What would I do to find the answer of 5?
Square root.
That's right. So if this is area, that means that it is units squared. And we have to remember, if we want to unsquare something, we do the opposite. We square root. So I'm just going to move our second example down a bit so that we can do this one. So the way to find the answer, if I go square root 25, that's going to find me my side length. Okay? And that's going to give me 5. Let's take a look at another example. Okay, here's our next example. So 6.25, that's my area. I want to know my side length. So if I want to know my side length is equal to the square root of my area. So now I'm going to go square root of 6.25. Now, it's a decimal. So do you think I'm going to get a decimal answer? Probably. Let's give it a try. What did you get? Exactly. The answer you get is a terminating decimal. A terminating decimal means the decimal stops. There's no extra numbers at the end. So this one's a terminating decimal. This decimal stops. 2.5. Done. So how can you check your work to make sure you did it right? What would be a strategy to check your work? Exactly. Work backwards. Take it as 2.5 times 2.5 or 2.5 squared. And we will get 6.25. And yep, that's how we did it right. Now, what if it was a fraction? Am I allowed to have a fraction that's a perfect square? Yeah, you betcha. As long as the top number and bottom number are both perfect squares. So let's take a look at an example like that. So example 3, we've got 49 over 64, and I want to know if that's a perfect square. So when I do that, we have to separate the top and the bottom. So I would put a square root sign on the top, and then I put a square root sign on top of the bottom. Okay? That's going to help me out here. Now, if I square root 49, what do I get? 7. If I square root 64, how big do I get? 8. Good. So my answers are both terminating decimals. The decimals end on the top and on the bottom. So that means, yes, I have a true solution. Okay? If one of the numbers was a run-on decimal, it wouldn't work. So let's try another example, one that won't work. So let's say I've got 72 over 81. Well, 72, if I take the square root of 72, somebody please do that for me. Round it to one decimal, please. 8.4? Does it round 8.5?
Yes.
Okay, so we're going to say 8.5. Now, the next one, we're now going to do, and again, this is a rounded, not exact. And then this guy here is the square root of 81. And how big is the square root of 81? 9. Good. So now, the top one is a run-on decimal that we had to round, but the bottom worked okay. It only works to be considered a perfect square if they both work. So this one is not a perfect square. Okay, it is not a perfect square. And it's because the top number gives us a run-on decimal. So that tells us right there then, what are perfect squares? Numbers that do what? They create another kind of number. Run-on decimals. Okay? So we're going to take a look at those non-perfect square roots. And that's going to wrap up Unit 1 here. So B is non-perfect. Non-perfect squares. They are run-on decimals. Now, there's a couple numbers that create run-on decimals. One of them specifically is, what gives you a non-perfect square? Pi, good. Automatically is run-on. So it is an irrational number. So non-perfect squares are numbers that will give you run-on decimals. So that would be any number that's not in our perfect square list. So if I were to make a perfect square list, they have identical factors. So 2 times 2 is 4. 3 times 3 is 9, and so on. These numbers don't fit that pattern. They don't have two factors that are identical. So these ones are run-on decimals. Okay? They are non-perfect square roots. So there's a number underneath. 16 is a perfect square. I could put 15 underneath. I could put 14 underneath. I could put any number that's in between the perfect square numbers. Those would all be non-perfect square roots. And those will always give you run-on decimals. Okay? Push pause now and play when you're ready.
Wait, you weren't paused?
This concludes the review for Unit 1, Powers and Roots.